are doing the coordination chemistry, in that actually we have reached till linkage isomerism, and that linkage isomerism I told you that hard and soft interaction, right? So in that hard and soft interaction, uh, we will see the how this will help. Okay, like if you see the symbiosis effect. Okay, so we'll see what is symbiosis effect. So that we were about to discuss. So in that symbiosis effect, you should know what is symbiosis effect. Generally, why we are doing and why we should know this symbiosis effect. Okay, because we should be able to understand in the octahedral or tetrahedral, not tetrahedral, in the octahedral and square planar complex, not in tetrahedral, octahedral and square planar complexes, which one is more stable, the cis form, transform, or like like the arrangement of the ligand to the metal. So which one is be more stable? So to identify that, we are seeing this, okay, this symbiosis effect, right? So it will see that applicable for octahedral complexes, right? It is applicable for octahedral as well as tetrahedral also, right? So we can write it is applicable for octahedral as well as square planar complexes, right? As well as for square complexes. Now, first we will see for octahedral, right? So for octahedral, we'll just see in this symbiosis effect. So in octahedral, it will be soft interaction and hard interaction. So only you have to find uh, in their 180-degree angle. Okay, will be like in there. You can write in there 180-degree angle. 180-degree angle means we can write that in the trans phase. Okay, in the trans phase, whether it is soft interaction or in there 180-degree, that is trans phase, hard and hard interaction should be there. Okay, either it should have soft interaction or it should have hard interaction for octahedral complex, because we are discussing the octahedral complex right now, right? Okay, this is if this is present, so we call it this is having symbiosis. Okay, sometimes directly question you will get whether the given compound is having symbiosis effect or anti-symbiosis, right? Now this is symbiosis. Now what will come under anti-symbiosis? The opposite of this. Suppose if if in there 180-degree or maybe in the trans phase, if I write in there 180-degree or in the trans phase, if you have soft and hard interaction. See, it will be more clear when we are taking examples. Okay, so just try to understand the concept first, because there is a limitless examples, right? So first we will clear the concept. So soft and hard means other than soft and hard. If you have, then that will be your anti-symbiosis effect, right? So this will show anti-symbiosis effect. So that is applicable only for octahedral complexes, right? If you see the square planar complexes, then it will be reverse. Just reverse whatever you are finding in octahedral, it will be reverse of octahedral. Okay, understood? So now, if you see here, if I take one example here, like suppose I'm taking, for example, if you have a complex cobalt NH3 5 times, and then if you have NCS, okay, so this is 2 plus, okay, this is suppose A, and if I take one more example like cobalt NH3 5 times, and if you have SCN, okay, 2 plus, this is B. Now in these two, if you see that NCS means it is directly connecting through a nitrogen, HCN means it is connecting through uh, sulfur, right? In this case, if you see, if I draw the molecule, it will be like cobalt. This is octahedral, right? So in this octahedral, if I draw this complex, so I can put NH3, 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 and NH3, and one is NCS. Now the second one, if I draw, it will be cobalt. See, always if you are having confusion, draw it and then see, right? So cobalt, NH3, 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 and it is connecting through S, C, and N, right? If you see, as I told you that 180-degree position, right? So 180-degree position, like in these two are at 180-degree position, right? Now you see this side it is connecting with nitrogen, and this side also it is connecting with nitrogen. If I take another color, so you just see it is having 180-degree angle. So 180-degree means this is the trans phase, right? I'm not saying that this is a trans isomer. I'm just telling that these two belongs to trans phase. If you see this compound, this ligand and this ligand, these two ligands are at their trans phase, means 180-degree angle, right? Now you just see here it is connecting through nitrogen, but here it is connecting through nitrogen. So both are connecting through nitrogen, and we know that nitrogen is hard, Lewis base. So here hard interaction, right? So we can write it here. It is hard interaction, right? Now likewise the second one, if we see, this is the 180-degree angle, means this is the trans phase to each other, right? As I told you in the for previous example, for example A, this is also not a trans isomer, but I'm telling that this is belongs, like we can say that 180-degree angle, so these two are in trans phase but not trans isomer, right? Now you just see here it is connecting through nitrogen, and here it is connecting through sulfur. Now nitrogen is hard and sulfur is soft, right? So here we can see the interaction is soft and hard interaction. Now the question is says that which one is more stable? Okay, which one is more stable? So always remember that, as I told you, we are dealing with octahedral, and octahedral, if you have soft or hard, that will show symbiosis effect, and that will be more stable. Okay. Likewise, you will have this anti-symbiosis effect, like soft and hard interaction, anti-symbiosis effect, and this will be less stable. So the stability order, okay, if you write the stability order here, the stability order will be your A will be more stable than B. Understood why A is more stable than B? So such type of questions it will arise, right? A will be more stable than B. Now, what is the relation between A and B? These are linkage isomers, right? These are not trans isomers. So these are linkage isomers. So there are two isomers, total two isomers. In that, both are linkage isomer, because this is a type of Ma5B type, right? Ma5. If I say the type of molecule is Ma5B, right? This is the type of molecule, and in this type of molecule, we don't have any geometrical isomers, we don't have any optical isomers, we have only one history isomers, that is self isomer, right? Now, in that case, in this case, we have one ambidentate ligand, right? One ambidentate ligand. So that's why this is having linkage isomerism. So total isomers will be two over here, right? Okay, understood. If you are having any type of doubt, you can let me know through. Okay. So I'll clarify it. So now you understood this is Ma5B type. Now going forward, we can write here C, as we know that A is more stable, so we can write that A is more stable thermodynamically. Okay, it is thermodynamically more stable. So we can say it's a thermodynamically more stable. This is more stable compound, right? Because hard interaction is there. And we can say that A is showing symbiosis effect. That is also one more question it may ask. A and B, which one is showing symbiosis effect? So A is showing symbiosis effect. B is not showing. When B is showing anti symbiosis effect, right? So likewise, if you see, if I say another example, see like the more number of example if you are discussing, the more clearer it will be, right? So if you see, if I give another example, so A compound is cobalt CN5 NCS 2 plus, and your B is cobalt CN5 SCN 2 plus, right? So here again it is connecting through nitrogen and it is connecting through uh, sulfur, right? So how? Let me draw cobalt, right? So we have CN, CN3, 4, and 5, right? And we have NCS. So this is molecule A. Now we have B. So cobalt 1, 2, 3, 4, 5, 6. Now we have 5 cyano 1, 2, 3, 4, 5, and 1 SCN, right? Now you just see this is molecule B. Now you have to find it out which one is showing symbiosis, which one is showing anti-symbiosis, which one is having hard-hard interaction, which one is having hard-soft interaction or soft-soft interaction. Anything you can find it out. Now it is an octahedral molecule. So in this compound, you have to find whether it is showing hard-hard or soft-soft. If it is showing soft-soft, then also it is more thermodynamically more stable. If it is showing hard-hard, then also it is more stable, right? So now in this case, if you see here also that the two different ligands are these two. So in these two, again, it is 180-degree angle. So we can say these are in trans phase. So here you just see it is attached with carbon. Here it is attached with nitrogen. And we know that the nitrogen is, I'll choose different color. Nitrogen is hard and carbon is soft. So this is soft hard interaction, right? Now what about here? Here you just see here again it is 180-degree. Okay, it means these are in trans phase. So we will discuss these two elements. Here it is carbon, it is soft. Here it is sulfur, this is also soft, right? Now to understand basically what is soft and what is hard, so what you have to do, you have to see the HSAB principle. Okay, okay. Now, this is soft soft. So the interaction type is soft and soft interaction. Fine, soft and soft interaction. Now, this is an octahedral molecule. So soft and soft interaction will show symbiosis effect. And if it is showing symbiosis effect, this will be more stable. So here hard and soft interaction means this is anti-symbiosis effect. That means this is less stable. Now the stability order you can write A is less stable than B. Understood? So in the linkage isomerism, you will generally find this hard and soft interaction. Okay, wherever the linkage isomerism will be there, this question will be arise whether it is having symbiosis effect or anti-symbiosis effect. Which molecule is, which isomer is more stable? Okay, uh, whether it is connecting through NCS or it is connecting through SCN. Okay, so that connection you should be able to identify, right? Understood. Now for the square planar, as I told you, this will be showing by octahedral as well as for square planar. So here just it is opposite. Just see here how it will show in square planar. So little bit different. Octahedral is quite easy. Square planar complexes. Fine. So square complexes, you have to be have this formula Ma2B2 type. Okay. Otherwise, cis trans it is not possible. So Ma2B2 type molecule, if you have, so you have two types of classification. One you will have cis, either you will have cis or you will have trans. Only these two type of isomers you can get it. Ma2B2 in square planar, right? We don't have any optical isomers in this. Now, if it is in cis, it will be anti-symbiosis effect. effect will be more stable. Little bit confusing. Don't worry about that. Now, for if it is trans, then symbiosis effect will be more stable. But these are not in the case of octahedral. Understood? These are not in the case of octahedral. But in the case of square planar, if your molecule is in cis fashion, cis form, okay, cis isomer, then you have to see whether it is anti-symbiotic or symbiotic. If it is symbiotic, then it is less stable. If it is anti-symbiotic, then it is more stable. Now, if your complex is in trans phase, then you have to find it out whether it is showing symbiosis or anti-symbiosis. If it is showing symbiosis, it will be more stable. It is anti-symbiosis, it is less stable, right? And how to find? You have to just find hard and soft interaction. So if you have hard interaction or soft interaction, it will show symbiosis effect. If it is show hard soft interaction, it will be anti-symbiosis. Okay, that point is not going to be changed. But here, the cis form will have anti-symbiosis effect more stable, and trans form will have symbiosis effect as a more stable form, right? So how to find it out? Just we will say one example. Suppose you have platinum square planar. I'm just taking square planar NCS connecting with NCS connecting with NH3 connecting with NH3. So you just see this form is cis form, right? If you see this is a cis form, like this is A, and another one I'll just draw B. Okay, here I'll write SCN SCN NH3 NH3, and this is B. Understood? This is B. Now, out of these two, how to find which one is more stable? So first of all, what you have to find, see, this is a square planar complex. First of all, you have to find whether this molecule, given molecule is cis or trans. Like both the molecule are cis. You just see, we have 90-degree bond angle with the similar ligand. So this is cis form, right? So we know that A is also cis form and B is also cis form. See the 90-degree bond angle, right? So cis form, both are cis form. Now what you have to find it out? We have to find it out the interaction, whether it is showing symbiosis or anti-symbiosis. Now, first of all, you should know this is a cis form, and for cis form, your anti-symbiosis will be more stable, right? Anti-symbiosis will be more stable in cis form, and in trans form, your symbiosis will be more stable. So now, in this case, you just see we have nitrogen is attached over here, and here also nitrogen. So nitrogen, here also nitrogen, here also nitrogen. So nitrogen is attaching to the 180-degree angle. So here we can say that hard interaction, right? Hard interaction means this is showing symbiosis effect, because as we know that hard or soft will show symbiosis. Now what about here? You just see here we have sulfur, here we have nitrogen. It means soft and hard. Here this is nitrogen, here it is sulfur. So here hard and soft. So basically it is going to be hard and soft interaction. Now if it is hard and soft interaction, this is anti-symbiosis effect. As we know, see over here, as we know, here you can see, if it is in cis form, your anti-symbiosis effect is going to be more stable, right? So likewise, here, this is a cis form, right? See, this is a cis form. So in this cis form, this is symbiosis effect. So this is going to be less stable. Here it is cis form. Here it is anti-symbiosis effect. So this is going to be more stable here. So B is more stable than A. Here the stability order we can write B is going to be more stable than A, right? Because for cis form, anti-symbiosis is going to be more stable. Yes, you are getting it or not? Got it, right? Okay, but if it is in trans phase, suppose another example I'm taking, one example I should take, otherwise you won't understand. So here, suppose I'm taking this is another example, platinum, okay, square planar. So it is connecting with NCS, sorry, I should take transform, not cis form, NH3, uh, NCS, NH3. Now you see 180-degree angle between the similar ligand. So we know that this is A. So this is in transform. right? Now the option B, you have NCS, sorry, ambidentate ligand. So SCN, here also SCN, here NH3, here NH3. Got it? Now this is B, and this is also trans. Right. Now what you have to find it out here, A and B. Okay, in this case, you just see here, A is having, just identify the molecule. This is hard, this is hard, this is hard, this is hard. So this is hard interaction, right? Understood? So here we can write it hard, hard interaction. Got it? We have hard interaction. Likewise, we have B also over here. Here, what type of interaction is that? You just see hard, you have soft, and you have soft. Now, in this case, what you are getting two types of things, like both are present. Here, all are hard, hard interaction, but here, hard, hard interaction, and then soft, soft interaction. So if this type of situation arises, what you will do, if suppose this type of situation is arising, then what you are going to do it. Okay. So in this case, you will just see the hard and hard, right? Understood? Here hard and soft. Then you have to look into the metal. Now platinum is, if you see the platinum comes under the group that is nickel, palladium, and platinum. Platinum is going to be the, like, if nickel is 3D element, suppose if you draw nickel, palladium, platinum. So this is 3D element, this is 4D, this is 5D. So as we go down the group, the softness will increase. Okay, as we know that HSBA principle, if you see there, the bulkiness, if the bulkiness means that if the size is getting increased, then the softness will get increased, right? So here, if you compare with like if you see the platinum is the softer side, right? Now you just see here softer side, here hard, here hard. Okay, so in this case, basically all are hard here, for all are hard. Okay, so in this case we are going to choose this one. Okay, so in this case we are going to choose A. So A is going to be more stable than B over here, right? A is having more stability than B over here, right? So that you have to look at in like what type of interaction are there. Okay, what type of ligand are attached with the opposite side, like in the 180-degree angle. So here in this case also, if you see, this is the 180-degree angle, this is the 180-degree angle. So that 180-degree angle, what all ligands are present, based on that we are finding here. Now in this case, we have to find the symbiosis one, because this is trans, right? In the trans, we have to find the symbiosis one, and symbiosis effect will give you the more stable one, right? Symbiosis will give you the more stable one. Got it? Yes. So I think today let it be this much only. We'll continue tomorrow with few more examples, and directly we will move. I think we are left over with coordination isomers. That's all, coordination isomers. Okay, and then we will move. I think next class only, after coordination isomerism, we will move towards the uh, different theories in coordination chemistry, like valence bond theory, crystal field theory, and molecular orbital theory. Okay, so we'll start with valence bond theory. Okay, after coordination isomerism. Okay, so thank you.